So, the quantum mechanical theory originally proposed for black body radiation was extended to the emission and absorption processes also. So, the essential postulates of quantum theory essentially include the interaction of the ions, atoms, molecules with respect to energy. Okay. So, what does it essentially say? That the energies of the atoms, ions, molecules, electrons, etc., they are always in a fixed in a certain discrete energy levels. So, when it changes its state, it absorbs or emits an amount of energy exactly equal to the energy difference between the two states. Okay. So, this is what we should be remembering. So, during transition from the energy state to from one energy state to another, the frequency mu, I have written here, it has slightly come this side, the frequency or the wavelength, that is lambda, denoted by lambda, of the radiation or absorbed, radiation emitted or absorbed, that is related to the energy difference between these states by the equation E1 minus E2 is equal to h mu, that is equal to hc by lambda, where E1 is the energy of the higher state and E2 is the energy of the lower state. This is essentially a statement of the quantum mechanical effect, that is photoelectric effect. So, for atoms or ions in the elemental state, the energy of any state arises from the movement of the electrons around the nucleus. This we have already seen earlier in the on the discussion during the electronic structure. So, such energy levels are called as electronic energy levels. Now, molecules are an aggregates of the atoms. So, molecules what they do is they, in addition to the electronic states, they exhibit quantized vibrational and rotational energy levels arising from the rotation of the molecules or functional groups of molecules around their center of mass. Here it needs a little bit of explanation. Normally what we expect is, if it is only electron, atom or an element, the electrons, single element, number of electrons are there, but electrons are located around the nucleus in a space, and these electrons can go to next higher energy level or fall down from the higher state to lower state by losing or gaining the amount of energy that is equal to the quantum mechanical system, that is whatever we depends upon the work function and things like that. But the electrons by themselves of an element do not in principle possess rotational and vibrational energy levels. That means, if you take pure atoms, pure elements, then you see the only energy levels 1, 2, 3, 4 like that. Now, if I take a group of molecules, for example, nitrate NO3, nitrogen is there, oxygen is there, they are combined into a mass. The total mass of nitrogen NO3 is 14 plus 48. 16 is the atomic weight, 3 oxygen, that is 48 plus 14 is nitrogen. So, 48 plus 14 is about 62. So, nitrogen NO3, the atomic mass is 62. It is a collection of 62 protons or protons and neutrons together. Okay. So, the electrons are not only affected by the nitrogen atoms or oxygen atoms, but they are also affected by the NO3 molecule, that is a bigger molecule. So, the electronic energy levels of each electron of nitrogen is affected by oxygen atoms present in the at the center of the mass, and those electrons of oxygen are affected by the mass present with respect to nitrogen. So, the all energy levels of each electron is not only electronic, but there are subdivisions of electrons, electronic energy level, where the electron can move with a little bit of freedom. These freedom levels of energy corresponding to different freedom are called as vibrational energy states, and each vibrational energy state also is associated with a number of still smaller steps, that is rotational energy levels. Okay. So, the every electronic state is associated with number of vibrational energy states, and each vibrational energy state is affected with a number of rotational energy levels. It is akin to imagining that you are standing on the first floor, ground floor of a building, and you want to hit a football on the first floor. Now, how do you reach the first floor? There are number of steps, right. So, when you kick a football from the ground floor to the first floor, it may not exactly land on the landing of the first floor. It may land 2 or 3 steps below, or it may land 2 or 3 steps above. So, the possibility of the football landing on the landing site of the first floor are more, but it will be very near that also. It need not be exactly on the first floor landing. So, the that is vibrational. So, if each step is again associated with number of smaller steps, then the football can land anywhere. That is first floor, that is its postal address, and vibrational and rotational energy levels are like street address or house address. Okay. So, basically what we are trying to say is an electron associated with a molecule can exhibit number of electronic and vibrational and rotational energy levels. Okay. So, the lowest energy state of an atom or a molecule exists at room temperature. Again, as I was explaining to you, the element can be in its natural state at room temperature. That means, at room temperature chlorine is a gas, oxygen is a gas, copper is a metal. Like that, the lowest energy state of a molecule at room temperature is called its ground state, whether it may be gas or it may be a solid, it may be a liquid also, like mercury. So, higher energy states corresponding to the room temperature, that is at higher temperatures. Suppose from 25 to I heat a material to 35 degrees, the energy levels will definitely be disturbed. So, when these energy levels are disturbed, the electrons will get excited to higher energy level, but it may not go to next electronic energy level. It may just change its position from one vibrational to another vibrational energy level. So, you supply enough energy for equivalent to the quantum mechanical difference between the two energy states, then it can move to higher energy level. Otherwise, they will be moving in a small jumps from one vibrational to another and one rotational level to another. So, higher energy states are termed as excited states. Ground state, so we have all the electrons located in the ground state. When they are excited, they are at higher energy state, they are excited states, and the detectors do the job of the electrons emitted from the photoelectric materials like sodium, potassium, alkali metals, etc. They release the electrons, and the released electrons get attracted towards the anode, generate the current when it is maintained at slightly higher positive potential. So, because they attract the electrons. So, detectors used in spectrophotometers, infrared spectrophotometers, visible spectrophotometers, fluorescence spectrometers, HPLC, etc., all work on the principle of photoelectric effect. These include, there are different types of photoelectric devices which can detect the radiation. So, we will study what are the different types of photoelectric materials, because they are the detectors used in spectrophotometry or in many other instruments. So, right now we have what is known as photovoltaic cells, and then we have vacuum phototubes, photomultiplier tubes, diode array tubes, and several other detectors. For example, you can look at this table, this slide. In the last slide I have shown you that the different different detectors are barrier layer photovoltaic cells, vacuum phototubes, photomultiplier tubes, diode array detectors, etc. Okay. Now, we will study these, we will not be studying the barrier layer cells and other cells, except the vacuum phototubes and photomultiplier tubes and diode array detectors in our next class to some extent. I will explain to you when we are studying the instrumentation for atomic absorption spectrometry. Okay. So, in now we are entering the main topic of our discussion, that is atomic absorption spectrometry. So far what we have studied are the atomic structure and the electromagnetic radiation. What are the effects of electromagnetic radiation upon the materials? So, that has given us a little basis for describing the optical components of a spectrophotometer, etc. That is important for us to understand the instrumentation of a instrument of a spectrophotometer or atomic absorption. Now, what we want to do is we want to concentrate on our main topic, that is atomic absorption spectrometry for the determination of metal ions. And this is an important aspect as far as the elemental analysis is concerned. I think all of you know that there are about 53 metals and in the periodic table. Several of them are in the form of anions also. I do not know how many of you are aware, but copper ion, hydrogen ion, and metal, cobalt, like that you would have studied in your textbooks, but you also are aware of a chromate ion, that is anion, isn't it? Chromate ion, arsenate ion, arsenite, phosphate ion, etc. Even such elements can be determined even if they are in the anionic form. So, atomic absorption spectrometry is a tool for us to determine not only metallic elements directly, but non-metallic elements also indirectly to some extent. So, regarding that chemical analysis technique, which is fundamental to the chemical analysis of the environment and then materials and then water, air, etc., with different applications, atomic absorption spectrometry is essential. It is required for almost all chemical engineers, mechanical engineers, metallurgical engineers, and then scientists and several other people, civil engineers also. Everybody is concerned with the metal ions and their effect on pollution, etc. So, we are going to study what is atomic absorption spectrometry, its instrumentation, and how we go about understanding the phenomenon of the atomic absorption spectrometry. Now, the phenomenon of atomic absorption was first discovered by Wollaston in 1802. What he did was he found out that the solar spectrum is all of you know what is a solar system. Solar radiation also we have seen. Every day morning we get sunshine, and the sunshine what we get until 1802 was supposed to be a continuous uniform beam of radiation emanating from the sun. But in 1802 Wollaston has made an important discovery that the solar spectrum was containing lot of dark lines, which was later confirmed by Fraunhofer, another scientist. That was in 1814. So, the discovery of atomic absorption was not known at that time. Okay. So, but what was till then thought was a scientific thought was solar energy consists of a uniform bundle of electromagnetic radiation. But then when he put it in a prism, put the solar radiation, make it pass through a prism or something like that, he found out that apart from the different radiations, there were also some dark lines in the solar spectrum, and that was in 1802 Wollaston, and subsequently Fraunhofer took up the study of the solar radiation, and what he did was he confirmed that yes, there are dark lines in the solar spectrum, number of dark lines in fact. So, but again Fraunhofer did not give any explanation for the existence of such dark spots in the white background. But down the line, again after a few more years, Brewster put forward the idea that these dark lines are due to the presence of vapors of certain elements in the sun's atmosphere. So, till that time all the dark lines were studied extensively, and people thought that okay, we do not know what it is, we will call them A, B, C, D, etc. And then so alphabetical marker, they were all known as alphabetical markers. These alphabetical markers were supposed to be something which we do not know, but subsequently somebody else may find out. So, the idea was what it could be due to. People did think quite a lot, and but only later it was found that there may be certain elements, substances emitting specific radiations. Of course, sun's solar radiation is supposed to contain almost all the elements, because it is a hot bed of very high temperature of several million degrees, and even at the core, outer core, it is around 8000 Kelvin, right. So, anything that is there in the solar system, so in the sun as a solar body, whatever is there on the earth must have been there, because earth is born from the sun, but on the earth has cooled down and so many metals have formed. But there in the solar atmosphere, solar disk, the temperature of several million degrees exists. So, most of them would be either liquids or vapors. So, the subsequent idea that the substance is emitting specific radiations, they may be absorbing the same radiation. Once the idea of quantum mechanics was born and took shape and took firm roots, people thought that if a substance is emitting certain amount of radiation at a higher energy, it can also absorb the same radiation. Why not? If it comes across the amount of same amount of energy. So, if a substance is emitting certain amount of energy, but it reabsorbs part of the energy, then that portion of the spectrum looks darker. So, a plausible explanation was put forward. So, what they said is, substances emitting specific radiations are also capable of absorbing the same radiation, causing the spectrum of dark lines in the bright background. This is a very important discovery as far as atomic absorption is concerned. Now, you can see this phenomenon was generally known as Kirchhoff's law. So, the Kirchhoff's law was used to deduce the presence of oxygen. Using this law, they said, okay, what they did was they took oxygen and then vaporized it, passed a certain amount of radiation, and without radiation oxygen intensity was high. When they passed certain radiation, part of the radiation oxygen absorbed, and they saw a dark line, that is reduction in the intensity. Similarly, for hydrogen, sodium, iron, calcium, etc. Now, the frequency what they obtained using synthetic materials on the earth, they were also the same frequencies used in the solar spectrum. What they had observed, I had explained to you that those dark lines were called as A, B, C, D, etc. and those dark lines corresponded to the specific wavelengths corresponding to oxygen, hydrogen, iron, sodium, calcium, etc. So, people deduced that the solar spectrum, so solar matter, sun must be having all these elements in the solar system. So, the experimental confirmation, how do you confirm it experimentally? See, trying to do experiments on the earth is different, but to confirm, we cannot really go and confirm physically to the solar disk and try to confirm. So, the experimental confirmation came only from electric arc or spark. What they did is they took two electric arcs and they brought them nearer, produced very high temperatures, and by applying high voltage. So, when the spectral source surrounded by vapors, so atomic vapors showed dark lines corresponding to different elements. So, Foucault in France also demonstrated the reversal of spectral lines. So, what is reversal? What is being emitted is also being absorbed, causing the radiation to look darker. So, a cycle of observations started in 1802 was completed with the identification of different elements in the sun's atmosphere using Kirchhoff's law and Fraunhofer lines, etc. I will show you what is a Fraunhofer line. Here you can see that the solar spectrum contains dark lines like this. These are the intensities. So, initially intensity is very high, suddenly there is a dip, and then again there is a dip, again it goes up, again it goes steady, again it goes down. like this, you can see the whole solar spectrum. But if you take a photographic plate, this is the energy figure drawn. But if you take a photographic plate and then take the photograph of the solar radiation, these are the dark lines what you would see corresponding to different wavelengths. I have put the wavelengths here at 4500, 5500, 6500, 7000, etc. And you can see that every line can be identified by a number of dark lines. That means as there are as many elements as there are in the dark lines in the solar spectrum. That means sun also contains the same elements from which earth is made of and from which we are also made of. That is what the Christian philosophy says, earth to earth, dust to dust. So, we are all made of the same astronomic particles as earth and sun. That means oxygen, hydrogen, nitrogen, all of us, we are all part of it. We also have the same this thing. Now, this is these are the Fraunhofer lines for different spectrum. Again, what are the elements identified are calcium and then holmium, calcium, iron, hydrogen, iron, and these are all different irons, lines, frequencies. Magnesium has been identified, all the elements that we know of have been identified apart from the molecules like oxygen O2 and water and H2O. Like this, whenever we study any astronomic body, we look at the spectrum of these elements to find out whether such compounds can exist on the sun or moon or Venus or Saturn or any other planet. This is how it is being done. So, in 1902, Wood repeated the experiments of Kirchhoff and Foucault and proved conclusively that by introducing sodium vapor in the optical path of sodium emission, what he did was he took certain amount of sodium, burnt it, and then it started burning, emitting radiation. Then what he did was, in the path of emission of the radiation, he put sodium vapor, okay, and this caused the sodium vapor absorbed that radiation, and the intensity of the radiation coming out was much less. So, the idea of atoms absorbing the same radiation that is emitted by the same element at higher temperature and absorbing the same at lower temperature proves the phenomenon of atomic absorption. So, the atomic absorption, what is the end result? End result is a reduction in the intensity of the radiation, that is important. So, by analogy with acoustic resonance lines, he also showed the possibility of using these resonance effects to detect traces of mercury. That is, in 1902, using the similar principle, he showed that traces of mercury could be detected in the environment. However, the potential of this technique was not recognized by analytical chemists and spectroscopists till 1924. But by about 1924, the idea of atomic absorption was fairly well known to the scientists, but still they did not know how it can be used. It was till that time it remained a scientific curiosity rather than the rather than a scientific fact. So, the fact that the atomic absorption phenomenon was known and the lines were available, atomic lines were available, and these were published subsequently by Angerer and Jose and later by Frein and Smita for indium, aluminum, etc. So, the idea of atomic absorption was fairly well established by about 1930. So, we will continue our discussion in the next class. Thank you.